to show examples on how all of these properties work for this integration process now. When we're evaluating or solving definite integrals, so something with those bounds from 2 to 4 and of this entire function, so far now what we have are these properties and basic rules. I guess these are more like rules that you can find on page 390. And all of these help us to just integrate by steps, something like this. Whoops. And then over here, these are other properties that we can use. If there's ever something going on, like for example, this is a definite integral from, let's say, 1 to 1, and we have this kind of function. Well, if it were going from a lower bound of 1 to an upper bounds of 1, then we're going to get 0. So whenever something is kind of goofy in the integral, that's when we can use something like this. Okay, but these and these are the basic ones that we're going to be using in these example problems. Alright, so looking at this problem number 39, what I'm going to first do is use this, the integration of sums and differences. So if you're ever trying to integrate something with many terms, you can break them up. So this is what this is going to look like. No, I'm going to write down here. Okay. Alright, so now what you can see here is that I've broken each one of these terms up individually and written them as their own kind of separate differential, and then therefore I'm going to integrate each term separately. So I'm going to have to roll this down. Alright, so now what all of this amounts to is, well, first of all, what I'm going to have to do is pull out any constants that I can. So here I have constants in every single one, so I'm going to pull them out. So what I'm going to get is that 1/2 comes out to the front, and what I'm going to be integrating is just x cubed dx minus that 3 is going to come out front. And then plus, and then that 2 can also come out front. So what we have left is 1 dx. Okay, now I want to kind of say I can put a 1 right here for, these are what they gave us to use. And so now going back, what we can go ahead and say is, alright, if I could have integrated this and used that fundamental theorem of calculus, and this is what I would have gotten. Really though, we're just using those properties, so what I'm saying is this whole thing from 2 to 4 of x cubed dx, when I integrate that, it's going to be 60. So what you can go ahead and say is, alright, this whole chunk is equal to 60. So, whoops, I didn't do my 4 to 2. So what I can just say is this is 1/2 times 60. That was my first term. And then minus, I can go ahead and change. Now I'm going to go start filling in this piece, minus 3 times 4 to 2x dx. That's where I'm going to use this. So it's going to be minus 3 times, and then 6 apparently. And then this is plus, and then 2 times, and then it says that when I have the integral from 2 to 4 of just 1 dx, then it's going to equal 2. So it's going to be 2 times 2. Alright, when all this is said and done, what I'm going to get is 30 minus 18 plus 4, so 16. Alright, so that's all this was asking me to do. And if you kind of look back, what I did use was the integrations of sum and differences. I also used the scalar multiple rule, and I mean, I just used the idea that if you knew what the integral, the definite integral evaluated, if you knew what the evaluation of a definite integral was equal to, then you could just go ahead and sub those in. Okay, so those are using properties at its finest. Alright, the next problem that I'm going to be setting up is number 41. And so they gave us this information, and then what they're asking us to do is find and evaluate these definite integrals. So there's also a C and a D part to this, but I'm just going to start you off with the A and B. So really what we're going to be looking now at what we're really going to look at now are these properties on this side. What's happening here is they're giving kind of a segment. If you can picture this on a scale, what we're looking at is like a function like this. And I'm going to move this over. So just kind of give it a graphical explanation. Maybe we're looking at something like this, a function like that. All right, and that's our f of x. Okay, and then what they're saying is they've given us the area under the definite integral from 0 to 5. So 1, 2, 3, 4, 5. They said this segment right here is about 10, all right, units squared. But then they go in further and say, but over here too we have an area up until to 7. So this goes all the way to 7, but they do break us up into an interval from 0 to 5 and then an interval from 5 to 7. So what our properties do allow us to do is kind of work along those lines. So I'm going to move back up here. Okay, so given that information and then these properties that we're able to use, what it gives me is they're asking us then, I only have these two known definite integrals, and they've already been evaluated for us, but now they're saying, all right, let's put some of these properties together and say, what's the integral from 0 to 7? Well, for this first one, I'm actually going to use this property right here that, sorry, this isn't very big. Alright, it says from 0 to b is going to be equal to, if c is some sort of breakup between a to b, and you go from a to c and then c to b, so overall you're going to a from b, or overall you're going from a to b, but it just so happens that you have this broken up, then we can just add these. So therefore, overall, I'm asking 0 to 7, and yes, there's this breakup of 5 in between, but we can just add these up together, so for a total area of 13. Okay, and then here's another property that we would use. So normally, remember, our lower bound would be on the bottom and our upper bound would be on the top. But notice here that our lower bound is a higher number than 0. So what they're asking us is, they're kind of asking us to go backwards. From 0 to 5, the area was 10. But here is something that's a little bit strange. If you go from 5 to 0, you can't really evaluate that. So what they allow us to do by the property up here, sorry, I keep going back and forth. But what they do allow us to do is, if it happens that your lower bound is the lower number appears on top and thus the higher number appears on bottom, which should be the opposite, it should be lower higher, then you can rewrite this as this: negative, and then from 0 to 5, rightfully, f of x dx. So what this would be, now we do know what that integral is, so we could just write this as negative, and then this definite integral was evaluated as 10, so we get, whoops, negative 10. Alright, so that was your answer to part B. Alright, so you're really just fully using these properties and then also these rules to do some integrations here. Alright, the last one I'm going to do is number 45. And what I want you to keep in mind are the objectives of this one section are to link that idea that the area underneath, or an area bounded by some sort of function, can be found by doing integrals, so definite integrals like this. But the thing is, if you can avoid doing all this work of either the limit notation or integrating, finding the antiderivative and using that fundamental theorem of calculus, if you can avoid that, then go for it. And if you can see that there's just some sort of geometric figure that you can calculate, then go ahead and just use that geometric formula. So right here for 45 part A, what I am going to do is, this is a section of that very weirdly shaped function that they have for us, but what I'm only interested in is that from 0 to 2 range. So this is the only piece from x equals 0 on to 2 equals 0. This was the area that I was trying to find. Okay, and one thing we will be getting more into is if you ever have an area that's underneath the x-axis. I know it's kind of strange, but when we're doing integrals like this, we actually call them negative. If there's ever an area or a piece underneath the x-axis, it's a negative area or negative space. And I actually don't think I have too many problems like that, but this is going to be one of them. So if you do catch that in the back of your book, why it's negative, it's because it's underneath the x-axis, and we'll get more into that eventually. But here what I'm going to have you look at is this right here is a part of a circle. All right. Otherwise it would have gone something like this. So we know the area of the circle. Sorry, really bad. Area of a circle would be pi r squared. Okay, so we actually know the radius of the circle, so instead what I'm going to say is this is all going to be equal to pi and then 2 squared, but notice this is only a quarter of a circle, so I'm going to go ahead and divide this all by 4. So what you're going to go ahead and get is the area that's located here. It's a quarter of a circle with radius 2. So when all this is said and done, we get pi. However, when we're looking at this function, the function does indicate that we have this area underneath the x-axis. So what I'm going to go ahead and say, this is negative pi. It's a negative amount of area. All right. So what this 45 is going to make you do, it's going to just make you do bits and chunks all the way through. So I guess let me go forth and let me go ahead and do B with you. B is asking us to find the interval from 2 to 6 f of x dx. So what we also have is like a triangular piece. Okay. So here's an area. Once again, I'm not going to try to, I don't even know what this function is. There's bits and pieces to it. So what I'm going to go ahead and just say is this is a triangle with a base of 4, height of, let's see, what is the height? Height of 2, because this is 4 comma 2. So what you're going to get is 4 times 2, and then divided by 2, because this is the area of a triangle, how that's given in the geometric formula. And then so what you can say is this is going to be, if I ever asked you now, what is the integral from 0 to 6, what you could just do is add up these geometric figures. You could add 4 plus negative pi. So let's, whoops. This right here, if you were asked to do this, it would be 4 and then plus negative pi, and then you would just have to say, alright, that's just 4 minus pi, and you could keep it at that. Alright. Done.